Hi, I'm Beining Wu. I'm a PhD student at University of Chicago Statistics. And today I'm going to talk about some recent progress in polynomial approximation and distribution space, and especially some of its applications in learning theory. And this work is generally done with Professor Frederick Kohler from Chicago Statistics and also Data Science Institute. Now, before we get started, let's gather some motivation from learning theory on why polynomial approximation itself is important. So a long-standing problem in learning theory is agnostic learning, where given unknown distribution, we want to identify the sample complexity to find a classifier that can compete with a known function class, in the sense that the error of this output classifier is almost the best classification error achievable by this function class up to epsilon. And a typical approach is based on polynomial approximation. So if we can find a low-degree polynomial that approximates the optimal target in L1 distributional sense, then we can essentially rely on polynomial regression and thresholding to achieve this goal. However, in general, it is very difficult to find a polynomial that approximates well in the general X marginal setting. So later, people introduced a relaxation, which is called smooth agnostic learning. And in this setting, we only need to compete with the best Gaussian corrupted error of the given function class. And with this target, it suffices to approximate the Gaussian smooth function instead of the original function. And the critical role in this line of analysis is the degree of the approximating polynomial to achieve epsilon approximation error. And this matters because the degree typically determines how many monomial features we need, and therefore determines the sample complexity through classical VC theory. So in order to get the degree, a basic question is how fast does the best polynomial approximation error decay as the degree grows? And this is a goal of constructive approximation. And in several classical settings, it is well understood. So for example, like when distribution is compactly supported, and we have Jackson-type theorem that characterizes the approximation rate using modulus of smoothness. And for Gaussian space and some product measures where explicit bases exist, we can analyze how the coefficients of the function decays. And the difficulty starts when we move beyond these structure settings. For example, if we are only given a sub-Gaussian marginal distribution, then how can we identify a similar approximation rate? So there's been some work in this setting, like moment matching, that implies some sandwiching polynomials. And in the relaxed setting of smooth agnostic learning, we can approximate the Gaussian smooth functions by Taylor expansion. And the general question here is, how can we do constructive approximation beyond the strong structural assumptions on X marginals? Now, since our goal is to understand what is doable beyond sub-Gaussianity, a natural question is, how weak can we relax the assumptions on X distribution? For this, let's review the classical Colomans condition, which is a classical probability theory condition which says that if the moments of the distribution do not grow so fast, such that this condition follows, then the underlying distribution is fully determined by its moment sequence. And many familiar assumptions like strictly sub-exponential or sub-exponential distributions satisfy this Kahneman condition. And a classical relevance is actually that a classical qualitative result saying that under the Kahneman's condition, polynomials are dense in L2 distribution space. But for applications, qualitative density is not good enough because we need to know quantitatively how fast does L2 approximation error decays as the degree increases. So in the follow, we will work with the L2 approximation because L1 is essentially implied by L2. And as we'll see below, L2 brings some useful benefits in analysis. And in this work, we will try to answer this quantitative question. Now, to understand the starting point of the analysis, we should look back at the classical result saying that polynomials are dancing out to L2. And a key result in proving this is the Denjoy-Coleman theorem. Basically, it says that if a function class has slow-growing derivative bound, then any elements with all zero derivative at one point must be identically zero. And this class is known to be quasi-analytic class. And let's look at the argument below. Basically, if we take a function f and let R be its residual after projecting onto the polynomial space, we can define a residual transform psi, and all the derivatives of this residual transform at the origin are zero because the orthogonality between R and all polynomials. And given the moment bound, we can also show that this residual transform is quasi-analytic. And the Denjoy-Coleman theorem forces that this residual transform is zero, and it means that the residual itself should be zero. Now, this argument works for infinite degree, but for our application, we need to understand the finite degree approximation rate. So let's see what is this residual transform can give us. And we take Rd to be the residual transform residual after projecting to the degree d polynomial space. And analogously, we define this residual transform as psi d. And because of the orthogonality, psi d has a zero of order d at the origin. Now, the approximation error is the squared L2 norm of Rd. And by the Pythagorean theorem, this can be written as the inner product between the original function f and the residual Rd. Now, recall that the residual transform defined above is actually the Fourier transform of the residual times the density of the distribution. If we consider a simple case where the target function is the Fourier inverse of an integrable f hat, then this middle inner product can be formalized or can reformulated as an inner product in the frequency space by tangential real theorem. And the benefit of doing this is that we know that psi d has a zero of order d at the origin, so it should be small in magnitude in the low frequency area by certain smoothness. And on the other hand, for many smooth functions like Gaussian smooth targets, the Fourier transform it decays very fast, so the high frequency part can also be bounded. And therefore, the approximation error can be controlled by combining the low frequency cancellation and the high frequency decay. The follow-up question is, how do we get quantitative control for this psi d locally? And the idea here is to use the complex analysis. Let's first consider a strictly sub-exponential case. And in this case, the moment generating function has a global bound like this, which implies that psi d is an entire function with finite order growth. At the same time, psi d has a zero of order d at the origin. Then we can apply a standard complex analysis argument like we divided by z through d and use the maximum modulus principle on the disk and optimize the radius of this disk to get this bound in the middle. For general sub-exponential case, the function is no longer entire. Actually, the moment generating function in this case only exists in the neighborhood of the origin, around the origin. So psi d is analytic only on a strip. And to tackle this, we map the strip to this disk using a conformal map, hyperbolic tangent, and then apply a maximum modulus principle again, and we obtain the second bound. And for now, we've derived low frequency bounds in these two specific settings. Now we can combine this low frequency control with a Fourier decay of the target to get this theorem. Informally, this approximation error can be decomposed into two parts. The first part, so given the frequency threshold omega, the first term is the low frequency part, which is controlled by the residual transform bound stated below. And the second term is the high frequency tail, which depends only on the Fourier tail of the target function. And this is the main constructive approximation statement that will be used in applications. And to use it, we typically first choose omega to make the second term small based on the function structure, and then control the first term with the appropriate degree. I'll briefly mention some extensions here. For now, we've been doing things in one dimension, and in fact, same ideas can be extended to higher dimensions. And we only need to take all the one-dimensional slices of the residual transform along each direction. And along each one-dimensional slice, the same one-dimensional argument still applies. The second point is that the target class can be more... the second point here is that our framework actually extends to more general distributions beyond sub-exponential. And in that case, the bound on plus ID needs more delicate tools from logarithmic integral estimates. And since it does not appear in our application, I'll not go through the details here. And actually, the target class can be more general than the Fourier stereogist class, which is basically Fourier inverse of the target of integrable functions or finite random measures. Actually, our framework extends to the polynomially weighted Fourier stereogist class, which allows many functions with polynomial growth, like ReLU, which appears in application. And this requires some more preliminaries from function analysis, like temporal distributions. So I'll just skip here. Now let's go back to the application of learning theory. So the main application here is the smooth agnostic learning. And the analysis goal here is to identify the example's complexity to find a classifier whose error can compete with the best Gaussian corrupted error in the given function class up to epsilon. And the concept class we consider here is a binary function with low intrinsic dimension, which only relies on the k-dimensional projection of the input. And the k-reduction is the following. So after the Gaussian smoothing, the optimal target becomes much smoother, and in particular, its Fourier tail decays rapidly. Then our L2 approximation theorem gives a low-degree approximation, polynomial approximator to this smooth target, which further implies L1 approximation. And finally, standard L1 regression plus thresholding is enough to learn it. And the sample complexity is determined by the degree. And the result is summarized here. And in particular, we see that for strictly sub-exponential distribution, we get a polynomial type degree bound with polynomial dependence on the intrinsic dimension k, the smoothing parameter sigma, and accuracy, the log of accuracy, log 1 over epsilon. And for general sub-exponential distributions, the degree is exponential in these parameters, showing that the sub-exponential case is much harder to learn. In other words, if the input distribution is heavy tail, you need much effort to reduce this tail error. And now most of the prior results in learning theory is about Gaussian case or strictly sub-exponential case. And so this result broadly goes beyond the earlier settings. And we also provide a comparison table between our results and the prior result in the smooth analysis. As you can see from this table, prior work already handles strictly sub-exponential distribution, which technically is similar to the sub-Gaussian case. And in fact, the prior work requires bounded Gaussian surface area of the function class. And our result removes this regularity condition, and we only need the low dimensionality and the boundedness of the target class. In addition, prior work used a more direct L1 type construction using Taylor expansion of the Gaussian density ratio. In contrast, our approach is more of Fourier-based L2 approximation. Interestingly, our analysis provided a sharper degree characterization. In particular, the epsilon dependence is polylog in our result, and also our exponent in terms of the tail order parameter is better. So based on this comparison, we actually see that the Fourier analysis not only provided a more flexible framework, but also able to provide sharper characterization. Now I'll conclude this talk. Now, because of the time constraint, I'll skip some details of some other interesting applications of this framework. And here I just put an index of all these applications for you. And for example, we can apply our framework to get a quantitative approximation rate for general smooth functions. And we can also do this for ReLU or sigmoid, and to get the complexity of learning one-layer neural nets. And there's also connections to universality, which says that the approximation rate in Gaussian setting can actually be transferred to general strictly sub-exponential case for a certain class of functions. And also we have applications to testable learning and matching cryptographic lower bounds. And to conclude, the main takeaway here is actually a Fourier perspective of the polynomial approximation error. And from this perspective, orthogonality helps to control low frequency contribution, and smoothness helps to control high frequency contribution. And combining these, we deliver a general constructive approximation framework under Kalman type distribution with explicit closed form rates for strictly sub-exponential and sub-exponential distributions. And this is all of my talk. Thanks.
So while the next speaker sets up, maybe one quick question. So maybe just